examples. And in the latter half, we're going to talk about MXNet, also with few examples, some insight into the into detail of deep learning. So first of all, let's go over the installation. It might take you some time, so I'm compressing the installation of both packages at the front. So in case you've got some issues, we have half an hour in the middle, so hopefully I can help you to resolve them. Okay, so for xgboost, it's gonna be, what? Wait, how do I? So probably I need to go full screen here, but the title is gone. Yeah, I think, is it too small still? It's clear, it's good? Awesome. Hey, just let me know if I go over something too fast or if you think I have avoid too many necessary details. Okay, so anyone who has problem with the installation of xgboost? We're all good? Awesome. What about MXNet? Who still haven't got it installed in it? Okay, cool. So just let me know if like during the talk of MXNet or in between during the tea hour, you can come up to me and ask me about the installation you've got run into any issue. Okay, so I assume that everyone's good. Oh, by the way, MXNet, here we are offering only the GPU version because CPU version, sorry, because GPU version asks for a lot more effort in your own configuration on your system. So I would try to avoid that overhead. And today I'm not gonna touch all those computational expensive experiments. Okay, so assume, does anyone still need this? Awesome, I'll just leave it behind. Okay, so let's start with xgboost. So xgboost is a library. It's not only in R, it has a lot of interfaces. It was implemented in C++, and it has a lot of interfaces in Python, R, and Julia, and other stuff, and like Java. And so to install, it's pretty easy. It's on CRAN, pretty much the latest version. And I'll cover some of the detail about the model first. So xgboost is short for extreme gradient boosting. Despite extreme here, I'll talk about what is gradient and what is boosting. So the very, very basic idea is that it's a composition of two elements. The first is we need a base model. So to do prediction, we sometimes got linear regression or like tree-based model or SVM or whatever you like, or GLM and stuff. But no matter what the model is and how it performs, the prediction, so we can get the second part into play, which is called boosting. And the very, very basic idea is that if we think one model is not enough, we can try to add more other models and to boost our performance, which is called boosting. We'll get into the detail later. So xgboost is mainly a tree-based model. So tree is a decision tree or classification or regression tree or whatever names you like to call it. So for those who doesn't know really well about trees, I've got a really neat and very lively introduction here. I'm a fan of this web page, so I will just guide you through it a little bit. So here on the right, we've got a bunch of data. I think the data here they're using is some descriptions of the houses in either San Francisco or in New York. And the problem is, how can we classify if a given house is from San Francisco or New York, which is basically a binary classification. Yeah, I really love it. So you just scroll down, and the right part just change according to your action. If you scroll back, so first some intuitions, like, so for the data, they've got multiple dimensions. They've got the area and the price for each square feet, and the total price and other dimensions. So this is, I believe this is the area. So on the left side is from the houses from San Francisco, and on the right side are houses from New York.
Elevation.
Sorry?
It's elevation.
What's elevation?
Elevation. How high up
Oh no, I think they're listing the houses, like they are just stacking the data. So on the top is one data point with 744.8 square feet, I think. Wait. Oh, yeah. Based on home elevation. Yeah, thanks. Sorry about that. So this is one dimension of the data. So it's a comparison. Seems that they are really different, but on the latter part, it feels a little bit more difficult to classify it. For those who are like below 150 feet. So we're remapping the data. So on the y-axis, we've got the elevation as we demonstrated before, and on the x-axis, we've got the price per square feet. So now we're separating the data in a better way with an additional dimension. So this seems to be a valid separation. We draw a boundary. So on the upper part, we've got all houses are from San Francisco, and on this lower right, we've got all houses are from New York. But what do we do with this part? So also a issue that we need to figure out. So from the data, we've got elevation and the year it's built, and number of bathrooms, and number of bedrooms, and price, square feet, and price per square feet, and things like that. So now we can use a tree model to come into play. So we just remap the data somehow like a bar plot. Okay, so we can have a few guesses of where we should draw the boundary here. If you draw it here, where it's on the rightmost apartment of one from New York, this is blue. I'm not sure if it's clear enough. Can I zoom in this as well? I don't know, but it's going to break the visualization. Yeah, so you can also, if you have your slides downloaded, you can just also click that link, and you can see better on your on-screen. So this is one possible split we can have. So here we've got every apartment or house listed on the right side or from San Francisco. But yeah, so we've got a perfect classification on the right side. But on the left, we've got 111 versus 92, which is like not so informative. On the other hand, we can push the boundary to the leftmost where there's nothing on the left, but everything is on the right, which is going to be 111 versus 193, which is still not informative. So we can find a somehow balanced split in between. And on the left of the split, we've got 105 versus 40. And on the right, we've got 6 versus 99. This seems a bit better than the previous two, right? Also, we've got some issues like here, or maybe we can do better. Can we do better? Maybe with this feature, we are doing our best here. But we can keep going using price here, and we use price per square feet because the data offers us more than one dimension. We can go beyond that. We can make the best use of everything we have. Okay, so now it's like a process we say growing a tree. So a tree here is given a dimension from a data or a feature from a data. We find a split point, and we split the training data into two parts. So here, the first feature we're going to use is the elevation, as we have demonstrated before. We've got a split here. We've got on the left and right the training data split it into two parts. And then for each side, we could use two other different, on each side we use one different features. So on the left, we use price per square feet, and on the right, we use price. So we further split the training data, and we can see that now it's splitting the data from San Francisco and New York much better than, a little bit better than previous one, and this one is much better than the earlier stage, right? So now we are more purely having data flowing to the left side, and then to the right side we are from New York, and fewer from San Francisco. And we keep on doing that in an iterative process. We go further and further with different dimensions. And then now we can see that they are, so now at this stage, so you can see that there's almost no need to do any further split, because, so here if you see that's a tree, and every node here, we call it a leaf. So on every leaf, we've got like purely data from either San Francisco or New York. So given the data, we can, starting from the root, so we first check if its elevation is above our split or below our split. If it's above, we guide it to the right. If it's below, we guide it to the left. And we do that recursively through every internal node, every split we are going to encounter. For example, a data point might flow from root and to here and to here and to here down and to here down to the very bottom here. Yeah, it should match to this one. Yeah, so then probably it's from New York. It's a blue one. So yeah, so this is basically how we construct a tree model, and this is and also how we predict with a tree model. Okay, so making predictions, it's like we're playing some machine. It has every data point as a ball, and they are guided by the split points. And the feature, so every node check one feature, and that feature guides it to flow to left or right. For example, if you hover your pointer to, on this node, you can see its elevation below or equal to 91.9 feet, and there is above. So for example, a data point might flow down here, and they're classified into left is New York and right is San Francisco. And that is on the training data. But we know that sometimes if we're doing prediction, we are doing on the data that we don't have a label, or we don't use them into the training process to test the accuracy of our model. So it's called, here they call it reality check. Yeah, so we need to make sure that we're not just dreaming about our 100% accuracy that by risking the not so generative model. So yeah, after the process, we've got 89.7% accuracy. Well, if it's ideal or not really depends on the scenario that you're going to use the model or your expectation. Like, for example, if your previous model only gives you 70%, I would say this is a successful model. But if your another model got 99 accuracy, then I would say you still got some room to improve. Yeah, and that's basically how a tree model has been built and how we make prediction on it, and usually how we compare and how we justify our model's performance. Okay, let's go back to, yeah. So any questions at this stage? Awesome. Okay, so here are a few points on why we're going to use the tree-based models. Like, if you're from a statistics department, usually the first model you're going to learn is a linear model, linear regression or logistic regression. And tree-based model is usually a bit later part. So why people use tree-based model? There are a few advantages. Like, first is interpretable. If you go back to the demo we just browsed, you're going to see that for every data point, whether it's classified into San Francisco or New York, we can somehow like summarize the rule that how we classify it to be either this class or the other one. So it's interpretable. And second is it's efficient. It's a little bit abstract to say or to claim it's efficient here, but if you do an algorithm analysis, it is linear with your scale of input. Like for example, we have SVM, but which is more computational heavy than the tree-based model. Well, they have their own advantages, but this is one advantage that the tree-based model have. And third is accurate. So we're going to touch about this part later, but it's based on the accuracy is when you're comparing that against a linear model. One reason is because it captures the non-linearity in the data, because at linear data you have a bunch of features, but you don't get unless you do your own feature engineering, you don't get the interaction among the features. Like what we have demonstrated, we can first look at the price at the elevation, and we split the data, and we split further with either the price or price per square feet or other dimensions. So now we're splitting the data into 4 parts. For each part, the data has already considered the interaction between 2 different features, the elevation and the price, or the elevation against the price per square feet. And if we go deeper, it's going to have a long chain of interaction, which may capture more pattern or the inner wisdom from the data than a linear regression. So, and it's efficient to train, so it's not going to be too slower than a linear regression, so that people favor that. And another thing, it's a minor issue, but sometimes I find it really useful because there's no need to normalize. I'll explain it a bit. So because when we are looking at a feature, we only look at where to split the data. So that means if the feature is from 1 to 100, or it's from 1 to 0, or it's minus 10,000 to positive 10,000, I don't care. What I want to check is where should I put my split point. If you normalize your feature, like you rescale it, and you divide it by some standard deviation, or do whatever normalization operations, then the split point's position will just also be adjusted accordingly. Say, for example, if the split point is at 50 and the feature is from 1 to 100, if you compress it to 0 to 1, probably the split point is going to be at 0.5, which doesn't make a difference when we are training the data and when we are making prediction. So this is one good part, because there are a lot of models that involves a weight or involve some matrix computation that require carefully tuned normalization preprocessing. Otherwise, the weight is going to be very different, or the scale is going to be too large or too slow, may cause some issues in accuracy or the ease of convergence. But here, we just don't have that issue, so that's another advantage. It's a minor one compared to the previous one, but I think it's pretty useful. Okay, so that's the part introducing tree-based model. So, but sometimes one model may not perform really well. So what do we do? So one way is use a stronger one or make it stronger. This is one way to go. Another way is we can ask for help from the others. Like if I can't fight with a group of people, I call more people to him. Yeah. So probably then we're going to be stronger. And one thing is, because making one model stronger has a limit, but if you have a good way to get a bunch of models to work together, usually the limit is going to be higher. Also there's a limit, but it seems easier, and the limit is higher where you can get. So there are 2 ways that we can add more models. One way is we add them simultaneously. So we add a bunch of models together and ask them to make their own prediction, and we somehow aggregate their prediction by either voting or average or weighted average or do whatever you want. And one role model of this approach is random forest. But this is not what we're going to talk about. But this is so one way to go. It's a strong model, and really it's a simple idea. And another approach to take is we can add them in a sequential way. So we add one first, we see if it's good enough. No, it's not. Then we add one more. If it fixes the problem a little bit, maybe we add one more. So we just keep on that process. And this is what xgboost is trying to do. So it's in a very scheduled way, like very brief way, we can describe the algorithm as an iterative algorithm. So this is going to be the most tough part today. So I'll make sure I don't touch too many details. But if you think you are not getting what I'm saying, just raise your hand. I'll probably explain more. Okay. So we've got a y, which is a training label, and we've got x, which is the training data, and we are having a f1 with a previous process that we just demonstrated train a single tree model. And we calculate the residual. So let's define residual in a simpler way, which is the residual 1 equals to the difference, just the difference between the true label and our prediction result. And the next iteration, we're trying to fix the problem we just created. So maybe, well, usually R1 is going to be smaller than Y. Usually we got a small gap between our prediction and our true label. But then we try to use another model to fix the gap, the newly generated gap here. And then we get a new residual. We don't expect a perfect match here. So R2 or R1 or R3 or R whatever will usually never be 0. So we can keep that process, like go on and go on until you're satisfied or there's no room for improvement. So the idea here is every newly introduced f, ix, this is from the ith step, it improves from previous result that we got from f1, the first tree, to fi minus 1. So from the very first step to the previous step, and we get a residual, and we fit the residual with the next added tree. And we hope that through this process, we're getting closer and closer and to shrink the gap between our label and our prediction. Okay, yeah, this is the toughest slides I've had today. So, and we take one step further because this is pretty brief idea, which is not so concrete. So sometimes we replace the residual here by a loss function. So a loss function is our goal or our measure applied on our prediction and label. For example, when we are doing regression, we use a loss function of square root. So we are comparing the y minus our prediction, and to take the square of it, sometimes we take an average, or and we take a square root. We take a square root and over it, use this as a metric to measure how far are we from the true label. And when we're doing classification, we are using the logic loss, which is it's a little bit complicated to describe orally, but yeah, maybe you've got an idea. So and sometimes we measure it by the mean abstract error, which is another way to do regression, especially when our label are in a very extreme scale or something. So we don't use square root RMSE, but we're using MAE, the mean abstract error. So we play with various loss functions to achieve our goal and to help to train our model to meet our expectation. So this is a measure, like here is also a loss function. It's just a simple difference between the label and our prediction. But usually in reality, we just don't use it. It's too simple, and it's in some scenarios, it's not the way we measure difference. So here we replace the R1 with the L. We use this as an abstract symbol to represent the loss function we're considering for the problem. So this is why the label, and this is the prediction from our first tree. And then we keep on going up, and at the teeth step, the residual, or the measure of the performance of our model is represented by L, the same loss function label against the sum of all the models we have from the first step to the teeth step. So in this way, we call it an additive model. We add one model there, and we try to use the sum of the model and to approach to the true label. So what we can benefit from this formulation is that we can decomposite the right side of a summation to be all the sums from the previous steps and the model we have at this step. And then we can do an approximation. We have a loss function here in the previous step, and we do a Taylor expansion here so that we can somehow decomposite these seemingly very difficult to play with loss function into two separate parts. And what's better is usually the left-hand side, because we're doing that iteratively, so the left-hand side value we have already calculated and used it in the previous step. So what we have is a newer model, so we can separate the later part out of this complicated function, and so we can focus on the latter part. So this is an additive model. Also, we can optimize it in an additive way. So is there any questions or? Yep.
In this case, are we assuming that the derivative function, so function 2, 3, 4, is the same model? Or so if we start with the base model, is that the same model for function 2, 3, 4?
Yep. So the question is, are we having the same model from across F1, F2 to Ft? Is that right? Yeah. So because our goal is different, because the first tree we fit Y, and the second tree we fit differently the residual. So because we are somehow like we are using the same training data with a different label. So the model eventually grown to mature, they are not expected to be the same. And furthermore, as later we're going to see that we can add more randomness into the training of the data. Say we subsample the features or subsample the data points so that we introduce more randomness in it so that we avoid to have identical trees or avoid they are using the same information again and again. And to expand that, take a step further. Although xgboost doesn't offer the functionality, if you want to implement your own framework, you can have the first one is a tree-based model, second one is a linear regression, and third one is a neural network, and the fourth one is a SVM, like whatever you like. You're free to do so. Yeah, just it's not that easy to pull every pieces together. But yeah, so it's a very general framework. You can put whatever you've got, whatever ingredient you want to pull in and stir. And it's not going to give you too bad result, I believe. I don't have experience on it. Yeah, but here, so we train, here xgboost train every F is a tree-based model, but we may use sample data, and we have different labels, so trees are not expected to be identical. Okay, so this is a very brief summary of our model. So the model, how we make prediction, we just sum up the values output from the trees, because previously we measured our difference from the label using the sum of all the predictions we have from each tree. So what we try to optimize is what we call objective function. So this is a simple form. We have a loss function that depends on your mission. So what kind of mission are you going to accomplish, like regression or classification or learning to rank, whatever, or other creative missions. Okay, so the previous part was pretty classic. So there is a GBM package doing almost the same thing as what I have described. We are in the same framework. But what makes XGBoost a little bit faster and a little bit more accurate generally, as this is a summary from people's experience using industry and from the Kaggle competitions. In my experience, or from my own interpretation, why XGBoost? Why do you want to use XGBoost against some other implementations? So there are 3 reasons that I can see. That the first is we've got regularization. So here at previous one, the objective, we only consider the loss function. So that's the only goal we're going to have. We want to ease the gap between our label and the prediction. But sometimes we want to regularize our model to make it have a better power in generation other than overfitted data, or make it into a model which goes into a super deep tree that every leaf only according to one data point, which is meaningless because that's an obvious sign of overfitting, because we usually don't expect the same data point in training data and test data. If we fit the training data in a too fine grid, probably we're going to have problem in the test data. We also talk about that later when we're trying to tune the parameters. And also we're using both first and second order gradient, which makes it converge faster. Well, it's not trivial to see how we use gradient to construct a tree. Because time limited, we are not going to touch about this part. But there are various papers on it, so if you're interested, we can talk offline. I can point you to some of the papers or implementations, details about how we use gradient in a tree construction. That's, well, a very brief idea is that for every time an internal node, when we're trying to split, we try to split the data with a best split point. So how do you define a best split point? So first we scan all the features, and for each feature we scan a split point, and we somehow measure, we have a measurement on the quality of the split, which is related to the gradient we have here. So that's a very, very brief description of this whole process. Yeah, but I'm not going to go deeper here. And third is we prune on a fully built binary tree. So usually we set a goal, say I set a maximum depth of the tree, say I expect to have a depth of 6. So then we grow it to the bottom and we prune it back, because sometimes in the classical, some algorithms, they decide to stop or not to split at that node. But sometimes, well, it's not usual, but sometimes you may get a negative or a very small positive earning at a split, but later on you might have a very large positive feedback. So probably it's better to grow it to a fully grown tree, and then we look back to then prune out those unnecessary splits, which boost the accuracy. Of course, it has some impact on the speed, but we think it's a good trade-off here. So we take the approach here. So these are 3 points I think why XGBoost is a favor that if people want to use a tree-based model library. Okay, so enough of talks. Let's get our hands dirty. So is there anyone who arrived here late and don't have the data or don't have a code? Please raise your hand. Okay, so I'll give you a few minutes. So if you can see that clearly. So if you visit here, you can either click clone or download and download zip. Or if you're comfortable with Git, you can git clone. So it contains 4 different data sets, and the total size might be around like 200 megabytes, I forgot. But the connection here is good, so you should be able to have them on your disk like in 1 or 2 minutes. Okay, I'll put it on one side for like 5 to 10 minutes in case you're having difficulty here. Oops. Okay, so we're going to use one small size data to demonstrate how we interpret the model and how we briefly train a model. So anyone has difficulty in loading the data? We're all good? Awesome. Just set your work directory right at the root of the directory just created. Then you will be fine. Okay, so the data is pretty small. Has around 15,000 data points and 9 features. One column is the label. So we prepare the data, just a recap again. There's no need to normalize the data. So we split the data into 2 parts. The first 10,000 part, we use it to train, and later 5,000, we use them as a test data. We sampled it, so it's not a pure split on the original order. So we have x and y, x.test and y.test here. So remember one thing, that xgboost takes the input data in the type either a matrix or a sparse matrix from the matrix package, so that if you've got a data frame, hopefully you want to convert it to a matrix in data by data.matrix or by other ways you're comfortable with. Because in data frame, sometimes it contains too many data in different type. Because for each column, I can have them in a different type. We think we're a little bit conservative here because we want users to know exactly what they are fitting into the model, rather than I read a bunch of strings into my space and I fit it to xgboost and get a nonsense of result, and they claim, but no, your package is not working, something like that. It happens in the very early stage, but I think because our underlying algorithm also performs the best with numerical data. So yeah, to remember to convert your data into matrix or sparse matrix before you fit it into the model. Okay, next we're going to do a cross-validation first. I think this is the first step if you're using a algorithm that is not too hard to train or it doesn't take too long time. Because cross-validation, here's a brief demonstration of the idea that we cut the training data into several pieces. Here is a 5-fold cross-validation. So every time we do 5 experiments, for every experiment we take one piece out here to perform as a validation data set, or in that subtask we treat that as a test data set, and the other 4 are the training data set. And we repeat that on every experiment, and every piece has a chance to be the validation data set, and then we take an average or whatever measure you like to measure how our model can generalize on a data set it has not seen before. Okay, so we can perform our cross-validation here. So first we define our parameter. We set everything else as default, and we only define 2 things. The first is objective, as we have described. Oh, by the way, sorry. I need to introduce about the data a little bit. Some insight from the data is it's called human resource analysis. So it's a data set containing several descriptions of how an employee performs, how high is the salary, and our goal is to predict if it's going to leave. So we can load in the data and take a yeah, so the first column is our, how do I zoom in? Can I do this? No. Just toggle it in the global options. Appearance. Is it good enough? Awesome. Oh, it's kind of scratched anyway. So we have whether employee has left, is going to leave or not, and or satisfaction level, or what's his performance and last evaluation, or the number of projects that's achieved. Here's a link to the repository where our first data set, so you can have more detailed information on this page. So this is a classification problem. It's a binary classification. So let's come back to to the page where we're going to start cross-validation. So first we define our parameters. We put it into a list object. So we have its name as the name of a parameter and equals to the value we're going to fit into. So we have binary, logistic, and we have other parameters. We're going to go through them later. So this is the last function we're going to use for this binary classification problem. And the evaluation metric is AUC. So does anyone need me to explain a little bit more about AUC? Awesome. Yeah. So if you run your code, you're going to get a result like this. So here I only set it to a three-fold cross-validation and run it for 10 rounds, just as a demonstration because the data is so easy that we hit 99 in training and 98 in validation very fast. So how do you interpret this result is to train AUC. The AUC is our evaluation metric that we have set. You can also set it into accuracy or some other things you like. And this is the average across all three folds on the training data set. And this is the standard deviation that we have. So these two measures, we usually use them together because sometimes if we split the data not so evenly, that sometimes you get a high variance, or sometimes if our model overfits on some certain training data, and then it performs really bad on the test data, then the variance is going to be high. So it's a signal that we see if how the model is stable across different training data. And on the right side is the evaluation metrics statistics from the test data set. It's also an average across three folds. Okay, and we output the same thing because sometimes you might want to write your own function to select which rounds you want to stop. So we output it in a data frame so that you can just subset or you can search for the model that you like or the parameter you like. There are some parameters to consider. So I classify them into several types. The first is how many trees do we want? So because previously when we're introducing about boostings, we're keep introducing trees in it, but there should be a timestamp that we are going to stop at this point. So in rounds, as you can see here, we only train 10 trees, and that sets the number of trees that we're going to experiment or to train with. So here, every line represents the result by summing up the previous, say the third line here is the performance of a sum of the predictions from the first three trees. It's not a performance of that single tree at the third step. Because if it was not fitting the label, there's no easy way that we evaluate our performance. And it's less informative because we're going to use the sum of all trees anyway. And ETA, this is it has a theoretical insight, but I'm not going to touch it here. The ETA is, so we have a first tree, and every time we add another tree, we don't add the prediction in the full scale as it was generated. We time it by a smaller number. Say the second tree predict the data point as 2, and the first tree predict that data point as 10. If we add them together, we get a prediction 12, but sometimes we want to hold our step a little bit back and to time the 2 from the second tree by a smaller number, so we're being more conservative here. We only trust it by a portion, so we're not going to add 2 directly to it. Maybe say, let's say add here, default value is 3, then 2 times 3, 0.3, sorry, default value is 0.3, then we might only add 0.6 to our prediction, which keeps our model more stable because every step we're taking it in a smaller size, so we're gradually and slowly approaching to the label, other than if we take a step too large, probably we're the label's here, but we're taking a step over here. And next step, we're taking back again, and we're just like wandering around the label, but without the capability of converge to our goal fast enough. So yeah, that's the explanation of ADA. The default value here is 0.3, but according to your mission, if you think it just don't converge, you just tune it up. If you feel it's taking a step too fast, you should tune it down, something like that. And the depth of tree, we have first here the max depth, which by default is 6, which means how large a tree is going to be when we're training it. If you have a smaller tree, of course, it's going to be less accurate, but sometimes we see that it has more power in generalization because they only learn some maybe shallow knowledge of it without too deep interaction, but that keeps your model from overfitting. It's just a matter how you want to tune your model. Just keep it in mind. We'll talk about that later. And mean child weight, which is, you can think in a simple way that how many data we want for the 2 flows when we're doing a split. Say if here at this stage we have 10, and for a split we can only lead 1 to left and 9 to right. Maybe 1 to right is not necessary, and it's going to introduce some overfitting issues. Probably we can control how we want to split our tree by these parameters. Then we can introduce randomness into our tree. We can subsample our data points, or we subsample our columns. Well, I know the name is a little bit weird, but in the early stage, you were not designing them carefully, but now makes it a weird name, but I keep explaining it to people so that they know this is sampling the column, the previous one sampling the row, and we don't want to break our API, so we just keep it till today. Yeah. So if someone who's familiar with RAM forest, they also use this trick to introduce randomness into the tree so that somehow avoid overfitting and to avoid fitting the noises. And also we have penalty. So when we are here, so we have loss function, which is like RMSE or logic loss, but sometimes we don't want our model to overfit. So the 2 mostly used regularization are, the first is how many leaves do we want? Because like if we have a tree with 10,000 leaves, then it can fit every training data point with a leaf. And it's not going to be generalized on any other test data. So we penalize on the number of leaves, which essentially is penalizing on our split, because for every split, we're splitting the leaf into 2 leaves so that we're increasing the number of leaves. So this is one regularization. And second is we want to regularize the sum of square of the weight on all leaves. Say if there's 1 leaf making prediction, but it makes a prediction with a really, really high value, say it's going to a million, and it's expecting all the other trees pulling down that value. But we usually don't want to see that, because that's going to introduce a less stable or a less robust model into it. Because what if the later trees don't pull it down, or they feel comfortable with it, or with whatever reasons? So we want to hold it back to control the value of our prediction on every leaf in a reasonable range, and to penalize those going so beyond our line, so that these are 2 regularizations we have. They're controlled by gamma, and lambda. So we've got them in the doc, so I'm just mentioning them briefly. Okay, so after, yeah. So we can retrain our model with cross-validation with a little bit tweak in the parameters. Notice that we have added the max depth. Because the data is so simple and so small, we don't need a deep tree as by default size of max depth is equal to 6. And we can try with max depth equals to 2. And then we retraining I need to code them into, we'll code them up. And this is the result you may have, because there are randomness in how we cut the data, so every time you run it, it might have some small variance in it. So is anyone having difficulty here? Any questions?
I have a question.
Yeah.
Is that analogous to the usual gradient descent parameter?
Excuse me? Sorry, what? Same parameter?
Yeah, it's analogous to the usual parameter, gradient descent. You have a parameter.
You mean the default parameters?
No, like it is that. It's a gradient descent, right? Kind of.
Well, that depends. It's a trial and error stage that you can first play with default parameters, but if you observe that it's not acting ideally, you probably want to tune that. I'll talk about the tuning parameter ideas and how you usually tune the parameters a little bit later. Okay. Any questions? Hey, cool. So I'll give you 1 or 2 minutes to play with the parameters to see how result changes. Like with respect to the parameters I'll listed here. So to get a full list of parameters that we have, you can just query in your console, xgboost. We're in the arguments part, and the parameter, we have it. It's a little bit shorter version, but we have it online with a more complete version here. Yeah, so yeah, you can try to see if you set some ideas, like if you set max depth to a very high value, and if you set eta to a very high value, say like 2, 5, or max depth 10, how the prediction is going to be, you can play with these ideas. For example, I can also try that out. For example, we set it to 10. Just give it clean. Like 1. How we sit in our, it's not in our space yet. Oops. And then we check our primes. Prime. Yeah, so LS1 max depth is 10, which is like overkill for this data set. I was trying too fast. So if we keep training with this setting, we're gonna see that. So what I have here, my parameters, I have set the max depth to 10 and eta to 1, which is super aggressive. It's a little bit overkill in either the complexity of a model or either the size of our step we're taking. So what you can see here is if it's training really, really well, that it almost hit 100%, and now it hits at the 20th, but we're having difficulty in getting the same accuracy on test data set. If it push it even further, probably we're going to have a decrease in the performance. That's usually what we call overfitting, that we're having too complicated model, and we fit every data point some way, or we have too extreme prediction values so that it performs too bad in the test data because it only fits the variance in the data, if it's a noise in the data, but not capturing the underlying pattern in it. Okay. So then, after we've got a set of parameters that we like, yeah, we just use the initial parameters we've set here. So just set them and keep everything else as default. And we can use the function xgboost to train. We just drop the term enfold here because there's no need to set it. We are only training on the entire batch of the training data, not cutting it. There's no repeat training. And we set data equals to x and label to y, and also we set in rounds to 10. And we get our model after a very short period of time because the data is pretty short. And we get them the output. So here we don't have the standard deviation of our prediction. We don't have our performance on test data. And then we predict model, and on the test data set, we have the prediction of the same size as what we have on our test data. We can calculate our AUC by loading the AUC package. If you don't have it, you just install it pretty fast. And remember, if you want to use this package to calculate it, you have to turn your label into a factor type of data and call it ROC first and then AUC. So we can see our prediction achieves 98.4, which is pretty close, and to our cross-validation result in the first. Yeah, it's 98.5, and on the test data, we have 98.4. Yeah, this is one way that we check how our model performs and generates across different type of test data. So, well, of course, we're assuming that all the data sets are having the same distribution across all their features, but sometimes cross-validation and may be done in the wrong way. We'll also talk about that later, so that the cross-validation result you have seen here is a fake result. So sometimes it's also good to split something completely out of your training loop, even out of your cross-validation. And then after you've got a model, you've got your desired parameter, you train your model and predict on the set-aside data set and to see how it performs. Like, is there a match between your cross-validation test data set and your prediction on the test data set? Yeah. Well, I've already done that. Okay. So now comes to a more interesting part. We are going to interpret our feature importance. So xgboost offers a bunch of tools to help you to interpret your model. So we have first, we can calculate the importance of our feature, which is important for some people that are analyzing their business data. They want to have more insight on their model. So this is the interpretation on our data. We have 4 columns: the feature, the name of our features, and we have a gain and cover and frequency. So gain here is it's an idea that every time we split, we want to gain something from the split. Otherwise, there's no need to do that. So we want to gain to decrease the objective value that we were using, that, for example, the loss function. We want to optimize it the most. So this is a value measuring how much we have improved in terms of our loss function, in terms of our objective, by splitting on this feature. So we can see that by splitting the satisfaction level feature, we gain a lot comparing to the others. And remember that this data says about how an employee is going to make its decision to leave or not the company. We can see the satisfaction level is absolutely related to its decision, right? And later is time spent in the company and how well is its last evaluation. And then the cover means that how, well, it's something similar to gain, but it's like a weighted measure. And frequency is how frequently we see that in a tree. So these are three measures you can evaluate the importance by three different metrics. By default, it is sorted by gain. And then we can plot it. Well, I'm not an expert in our presentation, so it always plots it into small size. Yeah, so if you have more than, say, 100 features, you don't want to read through the table, so you can just plot it. We, of course, can only plot the top 10 or 20 most important features into it so that you don't squeeze your plot too badly. So, yeah, this is a very simple example here that we have satisfaction and sales and salary. Oh, salary is not an issue. I don't agree with that. Okay. And this is how we inspect the importance. So, so now here's the, but I think I'll skip the practice. I think I would like to finish it at 10:30, right? We're finishing at 10:30 for break. Okay. So I've done experiments with myself a little bit. There are parameters can change importance. For example, if we introduce more randomness into our model, the measurement frequency here is going to be changed because sometimes the feature is not included into a tree. Say, for example, if satisfaction level is not included, then maybe some other feature is going to take over its number one position and to affect their model building process differently. Yeah?
So for example, one boosting here, right? So you have satisfaction level and for example, salary. And those two are correlated, right?
Exactly.
Yeah, and then when features are correlated, like maybe some trees give when satisfaction level is selected and salary is not selected, then satisfaction level will count more and then salary will count less. So how do you handle that? Do they have an intuitive way of handling that in the model?
So you're asking that if two features are correlated, how do I see that? Or, for example, there's no universal answer to that because they can correlate it in various ways. Easier way is that they are just linearly somehow correlated with a very high correlation score, but sometimes they could also be that both of them are correlated if I split the average monthly hours in some way, then in that case, they are somehow correlated. So there's no very easy way to do that. My suggestion is to play with it with randomness and sample by columns so that, and you tune that, push that to somehow high value. Say if I sample only half of a column every time I build a new tree, and I see that somehow the salary boosted up in its performance, its frequency or gain or whatever, then probably that's an indicator that it was underperformed, underrepresented because of the existence of some other feature. Then you can make an in-depth analysis on a trees that have the salary or have without a salary and do analysis from that. I would say this is very, there's no straight and fast way to do that. It could be a complicated case, and when you're having multiple features, it's even more difficult to have an insight on that. Yeah. Yep. Yeah, so in case I'm offering you some wrong information, actually yes. Yeah, we'll just start with the document. So we have here the value part, value session. We have features, gain, and cover, and frequency. So for a tree-based model, or actually we also can use a linear model as base model, but today we only cover the topic part here. So gain here represents fractional contribution of each feature to the model based on the total gain of each feature split. That's what I have explained. So every time you split it on this feature, you're going to gain something. Otherwise, you won't split it because it has no positive feedback on your model training. So the amount of the gain you have across all the model relates to the gain here. I think that's in percentage. Yeah. Higher percentage means the more important predictive features. And second cover is metric of the number of observations related to this feature. So what is that metric of the number of observations related to this feature? I think this is how it. So the gain is it's more like a weighted, and cover is. Sorry, I forgot how cover is calculated here. I think I wrote the code, but I forgot it. Yeah. So we can talk offline, or in the next session, in 3 minutes, I'll check it out and answer. Sorry about that. And frequency is how a feature has how often it appears in the model. So it could be used in the root, or it could be used in the very low, close to leaf nodes. But yeah, we just count that how frequency it appears. Okay. So any questions? Okay. I'll continue. So this is feature importance. So we can also visualize a tree. Say here we have feature names. We use the column names from our training matrix, and model is the model we just trained. And trees, I can set it to 0, which means we use the first tree. Yes, it's a huge one because we set a max depth to 6. If we zoom in here, yeah, we can see that this is a root node, and it has a split. It's split on the satisfaction level, and yeah, I think the cover. I'll explain offline. I'll do more research on offline, but here cover will be higher, and will be lower as we split it. I think it's more close to how many data points we cover that every time we split. So left or right branches, how many data points flow to the left, how many branches flow to the right. I think that's similar to that. I'm not sure if it's weighted or not. I forgot about details. I'll check it out. But that's basically the idea. And again, from this split we have is 2,000. It's pretty high. And then we check the number of projects, or on this side we check time span, the company. We keep flowing down, and here at the 0, 1, 2, 3, and third layer, we have a leaf, and they make predictions, and the value is 0.36, like this. And yeah, we have, if you're really want to have a business insight, probably this is a starting point. But introduce another issue, because we are not playing with only one tree. We're playing with multiple, maybe hundreds or thousands, or even more. I've seen that. So visualize a tree, or visualize trees in one single page is not realistic. Oh, sorry, I've already got that recorded here, but I forgot. So cover is the sum of second order gradient from the data points we have. So it is weighted by the gradient of the data points flow to each branch. Is that clear? Yeah, okay, good question. And yeah, and then gain improvement from a split. There are too many trees. So inspired by one blog post we read in 2015, we've introduced, oh, what happened here? Okay. One function called xgboost plot multi-trees. So it is trying to merge multiple trees into one huge tree where every single node represents multiple possible features. So in this way, yes, even larger, but we'll just look at the root for all. Yeah, you can see that some of the nodes are having 2 or 3 or more features, and some of them only have 1. This means that satisfaction level almost appear at the root node for every single tree. It's an aggregation across all the information, across all the trees that we have. So this is a strong indicator that satisfaction level is extremely important in our data set. And then we can still see satisfaction or sometimes it's number of project. We can see here, I believe the score here represents how many trees has that on this branch and how many trees has the other feature on that. It's a abstract representation of the ratio of the frequency of these two features at this level, at this node, so that we can have a more interpretable figure here than if we plot all 10 trees together on one page, which is hard to understand. And further, if you think this is still too complicated, we have another thing to help you to understand more about your model. Even a single tree is too large. How do you do that? So we have a function to plot the deepness of a tree. So we summarize like how many leaves we have at every layer. You can see that the x-axis is from the third layer, which means probably first and second layers they don't have leaf anymore. And from third layer we start to have a little bit of leaves, and number of leaves keeps increasing to the 7th layer. And we have a weighted cover here, which means how many data points are guided to flow into this leaf, and finally we make a prediction on them. Although we see that on the 7th layer we've got most of leaves, but actually we have most of the data points stopped at a 5th leaf. This is an indicator that maybe we are using a tree that is too deep, because we may stop at the 5th or 6th layer. So we may want to tune the parameter down by 1 or 2. So this is one way that we can have a very brief and high-level summary of how our model looks like without looking into hundreds of trees and inspect every node's feature or the split points and things like that. Okay, any questions? Cool. Okay. Well, I'll leave this out. Probably change the depth. Yeah, I was intended to demonstrate how change of parameter is going to change the model complexity plot here, which has a little impact. Okay. And so next, we're going to talk about parameter tuning. I think this is actually the question that's being asked the most, but I often feel that if I don't explain the model in a good way, that the audience know what is actually going on underneath, that they usually can't understand the parameter tuning well still. So I'm offering a new data set which is much more difficult than the previous one, and you can try to play with it. It's from a Kaggle competition. It's of moderate size. It has 60,000 lines and 93 features and 1 label. And it has anonymous features. I was trying to use this data set in the previous session, but it makes it really hard to introduce interpretation with anonymous features. And it's a multi-classification. We are going to class our data points into 10 classes. Okay, so we just do really briefly, we assign our training data and our training label, and we set our parameter. We just set them differently. The first is objective. Because we're doing a multi-class classification, we use multi-subprob, which ensures that the output is in probabilistic, or they have another I forgot. I'll check the look up the doc. So if you want the prediction not in probabilistic, after the logistic transformation, you can also do that. And evaluation metric on a multi-classification, we don't have AUC here. Correct me if I'm wrong. I'm not aware of. So we use a multiple log loss here, a loss function, and we directly use as evaluation metric to evaluate our performance. And the number of classes, we have 9 classes. So note here that we have minus 1 here on Y, because xgboost, when it's doing a multi-class classification, it has the label start from a 0, and there are integers 0, 1, 2, 3, 4, 5, 6, 7, 8, and here. And you can try cross-validation here, but warning, it's a much larger data set, so it's going to take you like 1 or 2 minutes. If you want to push the number of rounds a little bit higher, you can try that on your own machine. Oh, anyway. So you can try that on your own machine. So sometimes people use n-fold equals to 5 or even larger or smaller. That really depends on how complicated your data is and how fast you want it to be. Increasing the number of folds here will almost linearly, no, it's not linear, it's a reverse relationship. It will drastically decrease the speed of your cross-validation, because for 3 folds, it has to do 3 rounds, and for 5 folds, you have to do 5 rounds, so that, the training is going to be slower. So we can see that, well, it's still ongoing, but the test data set, it's not, I'm not running entirely with a higher number of rounds here. Yeah. Well, the parallelization is for every single tree. It's not for cross-validation. Yeah, I will say that they are. I tried it personally. I see there's no big difference, especially like if you have A cores, but you usually don't do A fold cross-validation, which makes it not less natural. Yeah. So any questions? Okay. So what are the tunable parameters? I've already shown some of them to you. So we've got an online doc recording parameters in more details. So if you are wondering if we have these or if we have that, you can check this page first. Probably you're going to find what you need. Oh, wait. Did I just? Oh, I just shut it down, sorry. Actually, yeah. Yeah, so some basic ideas on parameter tuning. So where to look at first if you think your parameters are not offering you some very decent result. So first is objective. Make sure that you are really using the correct objective to train your model, because I've seen it a few times, not too often, but a few times before doing classification with RMSE. It works sometimes, but sometimes it still doesn't offer you the desired result. And evaluation metric says, for example, if you are trying to minimize the mean square root error between your prediction and Y, you just use that. Or sometimes you care about, you care more about when, like, I want to take a log of my label first and we calculate the distance by some weird metric. That's okay. You can define that. You can custom that in your code, but you want to make sure that you're using that to evaluate your output. So these are 2 first things that you're going to check. And of course, the ADA and in rounds. So make sure that you're doing good in the first 2 steps. And for in rounds, you may want to see, so for example here, we're still seeing a really fast trend of the improving performance as we are lowering our loss here. So maybe here we're on a fitting and we don't have enough number of trees to fit our model, to fit our data well. So probably you want to tune in rounds more. Or I think my time's limited. I only want to use like 10 trees. How do I do that? Probably you can try. I don't guarantee you can get a pretty good model, but you can try to tune up your eta, which is a step size we're going to take when we're introducing a new tree. So that's, well, it's something you can try to play with first. And then, yeah, we start to observe that how our model performs. The first issue, which is most commonly seen, overfitting. We might try some ideas. We can have shallower trees. We tune the depth of the model and the mean trout weight, which controls whether we split or not at some point. And stronger randomness, we subsample the rows and columns of our input data so that we hope to get rid of the noise of our data, so avoid overfitting. And then we can set stronger penalty to control the complexity of our model. And sometimes we can have domain knowledge because, say, satisfaction level is indeed related to whether he is going to leave or not. And the more satisfied he is, the less likely that he's going to leave. It's somehow we have a domain knowledge from our daily life. So we've got a special parameter here, is monotone constraints. We can set that this feature is positively or negatively related to our prediction goal, so that we constrain that so that we don't cut it into like 100 of pieces and to make a fit across all the trees and things, so that it's another type of penalty or regularization. But I just feel it's interesting to point it out. You can consider try to use it if you have the domain knowledge. And okay, on the other side, if you're on a fitting, so somehow we're just doing it on the opposite side. So we may want to have deeper trees and stronger models. We may not want to use too strong randomness, but remember that a little bit randomness can usually benefit your model, because with no randomness, your trees are always using the same exact data, same exact information. So that, for example, in the previous plots we've seen, the satisfaction always appears at the root node. If this feature has a strong noise or is strongly related to some other features, then it's probably going to decrease our performance. So weak randomness doesn't mean no randomness. So I usually use a little bit randomness to start and to see how my model fits the data. And weaker penalty, probably we don't want to tie our model too tight. And this is another interesting parameter. It's called non-parallel trees, where at every step, like previously when we were introducing boosting, every step we have a new tree here. Then we can take a step further every time we add a random forest into it. We add multiple parallel trees here. So our base model actually becomes stronger. And the second step, we also add another bunch of trees here, trying to boost on the previous average prediction. In this way, you have a much, much stronger base model. And if you don't boost anymore, you just, with step one, then this model falls back to a random forest model with the correct setting of subsampling and on the data points and the data columns. So this is something I may have a try if I feel my model doesn't fit well. Because this offers you a stronger base model, and probably you don't need that many rounds to boost your performance. Yeah. Any questions at this point? Yeah.
I guess it's not really a parameter tuning, but balance classes. Balance classes is something that you handle.
Here. Yeah, I'm going to talk about that. Yeah, next slide. Hey, good question. Good timing. Okay, and then we usually use cross-validation to evaluate our model, but sometimes you need to use it with cautious because first, maybe you're dealing with imbalanced data set. Sometimes we have extremely enormous number of positive labels, but with only like 10, 20 negative labels. So, or with multiple classification. So you have one class that doesn't really appear in your training data set or something like that. Then you need to be really cautious about that. So there are several ways to take that. The first is that you sample your data set. You do a stratified sampling for your cross-validation, which means every fold of your split of training data, every fold contains the same ratio as the entire training script of training data, so that the model somehow learns the ratio of the label as well. The other hand is for extremely imbalanced data, you might want to use another kind of loss. For example, in recommender system, we are facing the very imbalanced data set. For example, say if you're browsing IMDb, there are millions, tens of millions of movies. Probably you are only interested in thousands of them, or even just hundreds of them. So they're using a different objective to train the model rather than a log loss or some usual loss function that we're using when we're dealing with a usual binary classification or multiple classification problem. So, well, that's another field, but this is one idea I have. And you can set, say, learning to rank or other things to tune your loss function that are easier with an imbalanced data set. And second is, sometimes we might want to deal with time-sensitive data. So when we're splitting the data, be really sure that you're not predicting the past by the information from the future. You need to, I don't think xgboost CV function can offer that functionality automatically, so probably you're on your own because it's a really flexible way to split the data. We don't see a very general way to handle that. But just keep in mind, if you're trying to predict the sales prediction, don't use the August data to predict today's, right? And parameter tuning, it's basically a process of trial and error, or there are some other ways to automate this process. The first is grid search. Say, for example, I think the sweet spot could be between the max steps between 2 to 10 and the error between 0, 0.1, 0.2 to 1, and then I'll that's maybe like a 6 times 10, 60 grid. So I'll just search for every pair of the parameters and I pick the one that works the best with cross-validation or a splitted validation set. Or there are some techniques with Bayesian or other heuristic way to tune the parameters automatically for you. So there are other ways to consider. We don't have that in our package, but this is some information you might keep in mind that maybe they're useful for your case. Okay, I'll just cover this pretty fast. So we have something that speed up our performance is that originally when we were building the tree model, we have a feature, and the feature, say we have data of 1 million row, and that's a lot. Every time if we want to find a split for every feature, we're going to scan 1 million data points, which is a lot of work, and reduce the performance. And so here, if we somehow get a summary of the feature, which is a histogram here. So if we make a histogram, say we have a bin of 1,000, then every time we only need to look at 1,000 data points, which is 1,000 times faster than the previous one. So in this case, we reduce largely a large part, which is computational expensive. And another way is we can grow the tree. First is we set a max depth, which is the depth of the tree. Say usually we set it to 6 by default and 10 or 2, but that's a full binary tree. And we grow it to the full binary tree and prune it back. And there's another tool actually. It's from the other tool. It's called Light GBM. I'm not sure about if they have a Auc package or not. They of course have Python package, and their and we have learned from them, and we have these approaches that every time I do a split, I'm not aiming at growing the tree into a specific size or to a full binary tree, but on the other hand, we check every leaf, we just split at the leaf that we can have the best gain or most gain from that split, so that it could be a very biased tree. Say, for example, this branch is more informative, or it's going to help our model grow better, and we split again, and this leaf split again, and probably it's a leaf, and here's a leaf, here's a leaf, and it goes deeper. Probably it's going to like 100 layers or so, but it's not going to take you too long because we're not a full binary tree. So one issue it may suffer is that it could overfit because it has a so long train of interaction. But yeah, just if you feel it's overfitting, just go back to other parameters to see if you have lock in it. Yeah, and I think that's pretty much it. We've got a GitHub here. We've got a forum. We've just set it up recently and discussed xgboost.ai here. You can ask questions like how to tune my parameters is more casual than a GitHub issue page, because GitHub issue page is more related to development. It's not a place to help you to tune your model or things. But in discussion forum, we're hoping to build it to be a more active community, so that people are helping each other with more casual or like various type of questions that people are communicating. And we have docs here, and docs, you can find a link. I've already demonstrated that where to find your parameters, but this is the entrance for every other interface. For example, if you're not using R, that's totally fine. Everything I've introduced here are also available in Python or in Java or in Julia or some other languages that you might be using every day. And that's it. Thank you. We'll have a break for 30 minutes. So any questions, you can just ask me or come to me offline. Or